This is Introduction to Proofs, section 7.2. We're doing preview activity 3. So here, the preview activity asks us to look back at modulo n. So we'll rewrite the definition. The definition is that really, you don't need to watch a video of me doing that. You should go back and rewrite definition the definition on page 85, section 3.1. So state two different conditions that are equivalent to the definition. Okay, so there's two different things that are equivalent to the definition. So n divides a minus b. So two different things that are equivalent to the definition might be that a is equivalent to b mod n if there exists a k in the integers such that a minus b equals kn. All right, that's another way to say it. Another way to say it is that a equivalent to b mod n if and only if there exists a k in the integers such that a equals b plus kn. All right, they're almost the same thing, but they're both slightly different. They're logically equivalent. Explain why congruence modulo n is a relation on Z. Well, what does it mean to be a relation on Z? Well, you need to have three things. You need to be reflexive, symmetric, and transitive. So, why is the definition of congruent? Why is it reflexive? Well, think about, is A equivalent to A? Well, A minus A is always 0, and 0 always divides any integer. So n divides 0. 0 doesn't divide every integer. N always divides 0. So and n divides 0. Okay? So yes. Is it symmetric? Well, if n divides a minus b, then n divides b minus a. Because just multiply that by -1. So here, use like this definition here. So if a minus b equals kn, then b minus a equals negative kn. So symmetric. I'm not doing a full proof here. I'm just kind of like arguing and waving my hands a bit because of lack of time. Now, is it transitive? Yes. So a minus b, I'm going to use this definition here. So a minus b equals kn, and b minus c equals mn. Then add them together, and you get the b's cancel out. A minus c equals k plus m n. So it's sorry, you can't see that. So true. So it meets criteria of being reflexive, symmetric, and transitive. Okay. Where was I? Carefully review theorem 3.4 and the proofs given on page 86. In terms of the properties of relations, what does this theorem say about the relations of congruence modulo n? So, theorem 3.4, hey, it's proven on page 86 and 87 that modulo n is reflexive, symmetric, and transitive. So we don't have to even do the full proof. Fantastic. It's always great when something's already been done. Okay. Now, write a complete statement of theorem 331 and corollary 332. Theorem 3.31, a page in corollary 332. Okay, page 136. Okay, theorem 331 Corollary 332. Okay, I want you to do that. You don't need to watch me write out those things. You should write those things out. Okay, and then what am I asked to do? Write a proof of the symmetric property for congruence modulo n. Let's prove the following. Let a and b be in the integers, let n be a natural number. Now, I believe this might have been one of your homework problems some way back. So it might be good to go review that. I don't know if it feels, doesn't, I'll do it, okay, fine. All right, so claim. Congruence modulo n is symmetric. All right, proof. It's always good to kind of make your claim different from your proof so you don't end up with something you're trying to prove in your proof. Okay, so what are we trying to prove? We're trying to prove the symmetric property. The symmetric property is an if-then. So to prove an if-then, you assume the hypothesis. So let a, b be in the integers, and n in the natural numbers, such that a is equivalent to b mod n. Okay, then a minus b equals kn. Oh, gotta introduce k for some k in the integers. Okay, then multiplied by -1, b minus a equals negative k times n, which implies b is equivalent to a mod n. Done. That was fun. All right, that ends preview activity 3.